It should be streaming right now. So, hey everyone, this is Nishchay, and today I'm going to take the episode 5 on in the SnackDown prep series, which is number theory. So let me just confirm if I am live or not. On in the SnackDown, I'm live. So of course there is a code forces round running right now, so I don't think many people would be watching it live, as one person in the chat has written as well. Sadly I won't be able to attend because there is a code forces education round. So there are still 5 minutes remaining to go to the code forces education round. If you want to choose to go to that, you can absolutely do so, but do watch this video after the education round ends, right? So everybody who is here right now, just reminding you that there is a code forces education round. Anyways, the people that are not interested in giving that, welcome to this class on number theory, and this is the fifth lecture in the SnackDown prep series, the third lecture in the advanced level. But you do not have to know the previous lectures that I have taught you to understand this one. It is a entirely independent lecture. So do not worry about going back, knowing the prerequisites for this lecture, because there are none. I would be basically summarizing number theory in this lecture. So let me share to my slides. Just give me a second. Yeah. My camera would be turned off in my slides because my camera keeps obstructing whatever I'm writing in the slide. So yeah. Let me actually test if I'm able to write or not. Right. So yes, sorry about that. Yeah, sorry about that. So we will be starting with SnackDown Prep Series Lecture 5. There is beginner level going on as well. So if you are a computer programmer of a beginner level, you might want to go to the beginner level classes. There are 2 lectures out right now, and the third lecture, greedy algorithms and 2 pointers, is going to come out tomorrow. So if you want to study that, you can. In the advanced level, we have already covered matrix exponentiation and bitmask DP, and today we are going to go on number theory. Just give me 1 second as well. This session is going to be of 2 hours, so if you have any doubts at any point of time, do let me know in the chat. I will be checking the chat from time to time to see if there are any doubts. The doubts may be relevant to the topic or irrelevant to the topic. It doesn't matter. I will answer all of them. And yeah. If you know anyone who is weak in number theory or mathematics and struggles with that in computer programming contests, do recommend him this class. Because I'm going to be summarizing number theory as a whole, right? Let me check the chat now. So welcome everyone who is joining the class right now. Do invite your friends and do let them know that I'm going to be summarizing number theory today. So number theory is a simple study of integers, right? Many of you might be wondering what are the prerequisites to studying this class. You should know what an integer is, right? Like an integer, even if you do not know what an integer is, do not worry. Like I'll just tell you what an integer is right now. It's just all of the set of negative numbers and the positive numbers, like -8, -7, 0, 1, 2, 3, etc. This is it, and this is what an integer is, right? So I'll be starting from the absolute basics and going up until the advanced level. So of course this class is crammed up with concepts, right? There are going to be a lot of concepts in this class, and because of that I'm not going to give much time on each individual topic, even though they are easy to understand. Even if you are hearing about them for the first time, you will be if you are following properly, you will be able to understand what I am saying throughout this entire lecture. But if at any point you are not able to understand something, of course do write in the chat and ask me the doubt. I will rectify it when I can. But if it's taking a lot of time, do not worry. Just skip that concept for now. Come to the class at a later point and give time on that concept, or just search the internet for the concept which I am talking about, and you will be able to find very good resources on that, and you will be able to study from them. I'm saying this because I have made this class as a type of summary of all of the concepts I know in number theory. So I obviously think that it is going to be a lot for everyone, right? I don't think everyone will be able to grasp every individual concept that I'm going to teach. So just prefacing that, if you are not able to understand something, that's okay. You should put time on that concept later on. But right now, I'm just going to be jumping from topic to topic, right? So is that all clear? Yash Agarwal, hello. Darius Shah says hi. Hello everyone. And yeah, I will also be coding during this lecture, so do not think that I will be just rushing through the lecture entirely. I'll be showing how to code these things, what kind of questions come up on this kind of concepts, and I will be sharing practice problems. I won't be doing practice problems in the lecture because there is a time constraint, but I will be sharing a lot of practice problems for you to solve, so you can go on there and solve once you complete this class. Hey everyone. Let me actually turn my cam on for this one. So if everyone is ready, let me actually go forward with the lecture, right? So let me go next to division, right? So this is the first topic that any number theory book starts with. But in computative programming, when you're learning number theory in computative programming, you don't even go on to this division algorithm, right? So let me first tell you what is the division algorithm. Wait a second, why is this coming on here? Right. So division, of course, number theory, here we will be studying integers only, right? So whenever I talk about a number, I'm talking about integers. There are no fractions in this world. 3 by 5, those kind of things doesn't exist. Rational numbers, irrational numbers like pi, that doesn't exist, and complex numbers surely doesn't exist. There just exist integers, simple and quiet integers, right? So we are going to be studying only integers. So in division, given a and b, where b is greater than 0, what does it mean to divide a by b, right? To divide a and b, we say that there exists q and 0 less than equal to r is less than b, such that a is equal to b q plus r, right? Here we say that we divided a by b, where q is the quotient and r is the remainder, right? Important thing to note here, that remainder here is always positive, right? So even if I take an example like a is equal to -5 and b is equal to 3, the b has to be positive. So if I take a is equal to -5 and b is equal to t, the quotient will come out as -2 and the remainder will come out to be 1. This is because 2 into -2 into 3 plus 1 is -6 plus 1 is equal to -5, right? So the remainder has is always positive and less than b. Sorry, not positive, non-negative, and the quotient can be any integer, right? So a is equal to b cube plus r. This way of writing from a and b is called the division theorem, and we can write q as a by b floor, right? So what I mean by this, if we have, let's say, a as 5 and b as 2, of course q here would be 2, right? And r would be 1. But if we divide 5 by 2 normally, we get a 2.5. So if we take the floor of it, we will get a 2, right? So quotient is always equal to a by b floor, and r is equal to a mod b. We can write r as a mod b. Mod symbol is just to denote this remainder when we divide a by b, right? B divides a or b divides a. This is just a symbolic form for b divides a. Let me show the symbolic form. It's just a single stick between them, right? We say that b divides a or b divides a if a mod b is equal to 0, right? That is, a is equal to b cube plus 0, right? So there is some q such that multiplying q with b gets us a, right? So then we say b divides a, or b divides a, or b is a factor of a, or b is a divisor of a, or a is a multiple of b. There are multiple ways to write this, but basically what that means is b divides a. Basically a modulo b is equal to 0, right? In code, we do not write a by b floor or a mod b, right? In code, what do we write? Instead of writing floor of a by b, in C++, if you are dealing with integers, you just write a by b, and that is a single floor division. You do not have to do anything else, right? But if you are in Python, you have to do a by b, right? There is a double slash here. Here you will just write a single slash. If you are dealing with integers, if a and b are already of the type int, in C++ you can just write a by b to get the question, and you write a mod b as a percentage b, right? A mod b, you read this as a mod b as well. In both C++, Python, Java, I think in around every language, this is the kind of standard in which you write a mod b, right? So this is the division, but there is one thing that you should note of. In C++ and in Python, I think it happens in Python as well, but I'm not so sure, so I'll be talking about C++ right now, right? So in C++, you have to be careful about dividing negative numbers, right? In negative numbers, in the example that I told you before, let's take that again. Example is a is equal to -5 and b is equal to 3, right? Here we saw that the quotient was supposed to be -2 and the remainder was supposed to be 1, right? Because remainder is less than equal to 0 is less than 3, and -5 is equal to -2 into 3 plus 1, right? But if you write the same thing in wait a second. So by this, what do we infer? That a by b floors is -2 and a mod b is 1, right? And this is correct. This is correct in mathematics, that a by b floor is -2 and a mod b is 1. Would be correct in mathematics, but in C++, what does it do? If you write -5 by 3 in C++, it will give you -1. And if you write -5 percentage 3 in C++, it will give you -2, right? Because what it does is it calculates this only, that is 5 by 3, and then it just puts a minus sign on the left of that. Same with here, it calculates 5 modulo 3 and then it puts a minus sign on the left of this. This happens, of course, if you write -5 and 3 like this, but it will also happen if you like initialize an integer a is equal to -5, b is equal to 3, and then if you write a modulo b, it will still come out to be -2, right? -2. Right, so you have to be careful about this, because this kind of works for us. That is why C++ has this implemented, but it is wrong in mathematical sense. So you have to take care that whenever you're taking a modulo of a negative number, make sure that the result is positive to be mathematically correct, and just check if a modulo b is negative. If that is negative, you have to add a plus b to make it positive, right? So is everything up until this point clear? Just write a yes in the chat if it is clear. I think everything up until this point must be, you must already know majority of these things, but just put a yes if it is clear, right? It would help me know how many of you have understood it. Kamal Pathak says yes. Mahashivishnu Chara says yes. Yash Agarwal says yes. Alright. So I'll just with this random sample of 3 out of 15, I'll assume that all of you have understood it. But if you have any doubt, just type it in the chat as I mentioned before, right? So let us move on from the division algorithm to prime numbers, right? What are prime numbers? Prime numbers are positive numbers with only two factors as one in itself, right? Most of you already know this, but here's the definition. Uh, the examples of prime numbers are 2, 3, 5, 7, 11, etc. Let's take 11 here. 11 is not divisible by 2 because 11 modulo 2 is 1. 11 is not modulo by 3, is not divisible by 3 because 11 modulo 3 is 2, and so on. So 11 modulo 11 is equal to 0 and 11 modulo 1 is equal to 0. Only these two satisfy this condition. That is why 11 is a prime number. If we take another non-prime or a composite number, any number that is not a prime is called a composite, except 1, right? 1 is special. But if we take a composite number like 4, right? 4 modulo 2 is 0. That is why there is a factor 2 which is less than 4 and greater than 1 for 4. That is why it is not a prime, and 4 is called a composite number, right? So prime numbers play a central role in number theory. So we absolutely have got to know how to find if a number is prime, right? How to find if a number is prime on a computer, not normally as you would do. How to find if a number n is prime in a computer. So to do that, we have multiple algorithms, right? To find if a number n is prime, that is called a primality test algorithm, right? Primality test. Those algorithms that find if a number n is prime or not is called a primality test. And there are multiple primality tests, working from the most naive. The most naive one would be like this, right? The most naive algorithm would be like this. Let's put a Boolean value here, which is prime. And right now, that Boolean value is true. That is, we are assuming that the n we have got is prime, right? Now what we do is we go from I is equal to 2 to n minus 1, right? And what do we do in this loop? We check if n modulo I is equal to 0. That is, if I is a factor of n or not, right? If this I is a factor of n, then we say that prime is false. That means the assumption that we took that this number is a prime is false, and finally we are just going to be returning prime. Return prime. Of course, we have to take care of the trivial cases, which is like if n is equal to 1, then what happens? If n is equal to negative, then what happens? I'm ignoring those trivial cases. I'm just explaining the main algorithm, right? So how much time complexity would this algorithm take? Of course, we have a single loop in here from I is equal to 2 to n minus 1, and there is only a single if condition here, so this is going to take big O of n time. Simple. Can there be an improvement done? You might have learned in your elementary school to find if a number n is prime. What you can do is, instead of checking from I is equal to 2 to n minus 1, you can check from I is equal to 2 to n by 2, right? That would reduce the number of checkings you have to do by a multiple of 2. This is the school method, as I would like to call it. This is the naive method. This is the school method because I remember I explicitly was taught this in school, right? But this is still very, very slow. This is still big O of n. There is no improvement to be done here. One other thing that you can do is take this concept to another level and check from I is equal to 2 to root n, right? And this is the what I call the square root method, right? In here, you only have to check the numbers from I is equal to 2 to square root n, and you do not have to check from root n plus 1 up until here we are taking a root n floor, right? So here there is a floor as well. We do not have to check from root n plus 1 up until n minus 1. We do not have to check these numbers to see if there is factor of n here or not, right? Why we do not have to check that? Because, let me explain that. If there, let us assume there is a factor of n which is greater than square root n, right? There is a d which is a factor of n, right? D is a factor of n, and D is greater than square root n, right? As D is an integer and n is an integer, and D is a factor of n by D would also be an integer, right? This will also be an integer. And what would be its value? As n D is greater than square root n, this value would be less than square root n, right? And this value would also be a factor of n, right? If D is a factor of n, then n by D is also a factor of n, right? And if D is greater than square root n, then we can say that n by D is less than square root n. So that means that we do not have to go up until D to see that n is prime. We can just go up until n by D, which is less than square root n, right? So only checking up until square root n numbers can suffice, and we can see if there is a divisor, if there is a factor of n in this set or not. If there isn't, then that means n is automatically prime, because there will not be any factor of n greater than square root n as well, right? So this is our square root time complexity algorithm, which is here, right? There are logarithmic time complexities as well, but I'll explain that in a bit. First, let us code this square root time complexity code algorithm. Let me switch my screen real fast. Yeah. So here we have already taken an integer n. We want to find if this n is prime or not. Let's take a rule prime is equal to true. We are assuming that the number is prime right now, right? If n is equal to 1, then we write n is equal prime is equal to false, right? Because n 1 is not a prime number. And then we go from int I is equal to 2, I star I is less than equal to n. Instead of writing I is less than equal to floor of square root n, which would take a lot of time, because we have to first compute square root. Square root has a time complexity of the square root function has a time complexity of log n, first of all, and second of all, the square root function will put precision errors here. So the square root function is really bad to use in code, right? If you're a real beginner, you can use it, but as you kind of advance slowly in competitive programming, you get to know that the square root function is actually very bad to use. So instead of using that square root function, we can use this kind of loop: I star I is less than equal to n, and I plus plus. If n modulo I is equal to 0, then we can just do prime is equal to false. And let us just output prime and see if this code is working or not, right? Let's take some numbers. 2 is prime, 3 would also be prime, 4 would be not a prime, 5 would be prime, 10 that's said as not a prime. Let's take a larger number, 1. This is a prime number. Let me take another number big like that. This is going to take a little bit of time. Actually, it's going to not work because this is not in the int limit. Sorry about that. Let's take a smaller number. This is also prime. This is not a prime. And let's take another number. Right? So this is a prime. So it's working as expected, right? It's giving out to be prime and non-prime for the numbers that you would expect it to. Let's take 69 as well. That is not a prime. That is a composite. That's 2 into 23. But the bottom line here is it still takes square root of n time to do so, right? It is still the maximum n up until you can apply this algorithm, this square root n algorithm. You can apply this algorithm up until a maximum of around 10 to the power 12 or 10 to the power 13 or 14, right? Up until like those kind of constraints. You cannot, if your given is that n is less than or equal to 10 to the power 18, you cannot apply this algorithm because in that case it would TLE. So To reduce that time complexity, there are multiple logarithmic time complexity algorithms, right? These are called logarithmic primality tests. And let me actually put this in a new page, right? So log n primality test, right? I am not going to teach them during this class, but they are really easy, right? You should study them. The most common one, or the most basic one, is Fermat test, and there are many others. If we are talking about complexity wise, there are many between the Fermat test and the next which I'm going to write, but this is the more significant one, Miller-Rabin test, right? If you understood Miller-Rabin test, you would not need to know any other primary test to, basically aid in your competitive programming journey. So if you want to learn about these primary tests, these are the names: Fermat test and Miller-Rabin test. You can go on and study about them if you want to, right? These are probabilistic tests generally, which means there is a probability that these tests will give a wrong answer, right? That is, if you apply a Fermat test on, let's say, 11, on 11 it will always output prime, right? On 11 it would always output prime, that 11 is prime. But if we run Fermat test on a composite number, let's take some large composite number which doesn't have a lot of factors, let's take 13 into 17, right? It might output prime, or it might output composite, right? It might output any of these two, right? But we can bound the probability of failure. Here the failure probability would be the probability that we get the output prime, right? In Fermat test we can bound that probability by half, right? And due to that we can run the Fermat test again and again and get the probability of failure very, very low, right? If you didn't understand what I said, do not worry. Basically what I'm trying to say, that you should learn these primality tests after this class, because they are really good as well, right? Let's come back to prime numbers. If you want to find prime numbers in 1 to n, all of the prime numbers in 1 to n, before we were finding if a single n is prime or not, that is going to take big O of root n time. If we want to find all of the primes in 1 to n, if we just use this complexity to run in here as well, that is going to take big O of n root n time. But we do not want that, right? That is a really bad time complexity. What we can do is we can use Sieve of Eratosthenes, which takes big O of n log n time, or big O of n time. There is a linear time sieve as well. We can use either of those sieves and basically find all of the prime numbers in 1 to n. Let's see what Sieve of Eratosthenes is. Before that, let me check for any doubts. Are there any doubts? Maharshi Vishnu says a modulo b plus b for n negative number. Yeah. So Maharshi Vishnu, as he's saying, if a is a negative number, what you should do is write a modulo b. That might turn out to be a negative number, right? So you should add a b to that to get a positive number, right? Anandandra says, well, this is not advanced. Yeah, I'm starting out with the basics. I will go up until like discrete root and primitive root and orders of multiplicative groups. But yeah, if time permits, then I will go on to that. If time permits, I would like to go on to Miller-Rabin and Fermat test as well. But of course, I'm covering all of number theory, so it might be difficult. Again, let's go on to Sieve of Eratosthenes, right? So Sieve of Eratosthenes is again a method that you might have learned in school, right? This method basically calculates all of the prime numbers which are between some 1 to n. What you do is first you initialize all of the you basically have an array of all of the numbers where you basically suppose that all of these numbers are currently prime. Here, when I have not done anything to these numbers, I'm assuming that all of these numbers are prime currently, right? Now you start with a loop where first you declare that 1 is not a prime. That is easy to declare, right? Then you go from 1 to 100, 1 to n, if you have an n, right? And check if the number right now is prime or not. We haven't reached 2, so we say that 2 is actually a prime. And then we cancel out all of its multiples. We go over all of the multiples of 2, which is 4, 6, etc. And we cancel them out because those will not be prime, right? 8 has a factor of 2, 10 has a factor of 2, etc. So all of these numbers, let me actually cancel out all of them, will not be prime. Right? These are all multiples of 2. Next, you go on with the iteration that you were going on. You go to 3, and this is also a prime number, so you cancel out all of its multiples as well. So that will be 3, 6, 9, 12, 15, 18, 21, 24, 27. If the number is already cancelled out, you do not have to cancel it out again. But you will still go on to the number to see if it's a multiple, if it's cancelled out or not, right? 33 will be cancelled out, 45 will be cancelled out, 39 will be cancelled out, 51, 57, 69, 63, 75, 81, 93, 87, 99. I think these covers all of the multiples of 3, right? Next, we go on with the iteration. We see 4 is not a prime number, so we will not go on there. But then we go to 5. This is still probably prime, and we have reached onto it through the iteration, so we declare it as a prime. And then we cancel out all of its multiples. So the multiples remaining of 5 are on this line, so we just cancel them out. Then we go on to 7. We cancel out the multiples of 7 here, right? So the multiples of 7 are 14, 21, 28. 28 is cancelled out already, I think. Yeah. 35, 42, 49. 49 was not cancelled. We cancelled that out. 56, 63, 70, 77, 77, 84, and 91. Right? So we cancel out 3 additional numbers by declaring 7 as prime. Then we go on to 11. We cancel out all of the multiples of 11. These are all cancelled out already. So we do not have to go after square root n. Right? You can still go after square root n to check if there are multiples remaining, but we kind of know that there will not be any multiples remaining after we have passed the square root n time, right? So we can just declare all of the numbers remaining as primes. So all of these numbers would be prime. Right? So this is what Sieve of Eratosthenes is, and the time complexity it takes is big O of n log n, right? So the time complexity this takes is, let me write it down here. The time complexity it takes is big O of n log n. I will not be explaining the proof because, frankly, I don't know the proof. I know that we can bound it by big O of n log n. Sorry, there shouldn't be an n here. It is an n log n, right? To bound the complexity by n log n, we can just write this iteration as n plus n by 2 plus n by 3, etc. up until n by n, right? So what I'm trying to say here, if we go on to 1, right, and go on all of its multiples, to go on to all of the multiples in 1 to n in of 1, we would require n steps. To go over all of the multiples of 2, we would require n by 2 steps. To go over all of the multiples of 3, we would require n by 3 steps, and so on, right? To go over all of the multiples of n in 1 to n, basically what I'm trying to say, to go for all of the multiples from 1 to n for k, right? To go on to the multiples of k, that is k, 2k, 3k, up until some tk, where tk is less than n. To go over all of these numbers, we would require n by k time, right? Around n by k time at least. It would be n by k floor, but around n by k time. So it would be a number like this, n plus n by 2 plus n by 3, and this is exactly big O of n log n, right? In the Sieve of Eratosthenes, we are optimizing it a bit more, right? In Sieve of Eratosthenes, we are only going over the prime numbers, so it would be like n by 2 plus n by 3 plus n by 5 plus n by 7, because we are not going over the multiples of the non-prime numbers, the composite numbers, right? So it would be something like this. So that comes out to be n log n. You can read about the proof of it if you want. You can search the proof of Sieve of Eratosthenes time complexity. It is a lengthy proof and it is very, very complex, and I don't think you will need it at any point of time. But if you are interested, you can do so. So a simple question: what is log 2 log base 2 of log base 2 of 10 to the power 9? Write in the chat what you think is the value of this. This is a ceiling function here. So you have to output the ceil of whatever value comes here, right? Up until then, let me check if there are any doubts in the chat. There aren't. That is good. Once you get to the answer of this question, just write it in the chat. This is a simple basic question which I just want to see how many of you are actually listening to this class. So Maharsh Vishnu Chavda says 5. Any other answers? Colonel Pathak says 5. Devang Bhagwat says 5. So yeah, the answer here is 5. Yash Agarwal says 5 as well. Good job everyone who answered, right? So the answer here is 5, right? You can just calculate log base 2 10 to the power 9. 10 to the power 9 is just less than 2 to the power 30. If you have been doing competitive programming for a lot of time, you kind of start to see, instead of seeing 10 to the power 3, you see 2 to the power 10. Instead of seeing 10 to the power 6, you see 2 to the power 20, because these are around the same value. This is 1024 and this is 1000, right? So 2 to the power 10 to the power 9 is just less than 2 to the power 30. So we can just convert this log base 2 10 to the power 9 easily to just write 30 here, and we just have to calculate what is log base 230, right? We know 2 to the power 5 is 32, right? So log base 230 and 2 to the power 4 is 16. So log base 230 would be somewhere between 4 and 5, tending more towards the 5 side. So it would be something 4.9 something. And the ceiling of that is 5, right? I said the time complexity for the Sieve of Eratosthenes was big of n log n, right? On what values of n do you think a linear algorithm works? If I had a big of n algorithm, up until what values of n would it work? It would work up until like n less than equal to 10 to the power 8 or n less than equal to 5 into 10 to the power 7, right? It would work for these values. Now I had a n log base n algorithm, and we have already seen that log base 2 of 10 to the power 9 is only 5, right? So for around these values, this complexity reduces to big of 5n, right? So this complexity right here is very, very optimized, right? This you can treat as just linear as well. You do not even have to think about this log n term here. You can just take it as linear and just write big of 5 in here. So you can apply this C for values as large as 5 into 10 to the power 7, right? Easily. But there is a big of n algorithm as well for Sieve of Eratosthenes. It is called sieve in linear time. It's not well that complex. It is very, very easy. That sieve in linear time algorithm as well. I did take it in a beginner course. You can read that if you want to, but most of the time this algorithm works, right? Let me show you the code for this for Sieve of Eratosthenes. I think, yeah. So let us initialize a prime, let us not write it as prime now, bool of f of n plus 1, right? This will contain whether I suppose that the current number is prime or not. Right now, all of the numbers I think are prime, right? I assume that all of the numbers are prime, so fi is equal to true for all I. Now, the loop, the actual Sieve of Eratosthenes loop that I write, before that I have to do f0 and f1 is equal to false, right? Because those are not prime. What I do now, I start from 2, I go up until n with I plus plus, right? And if fi, that means my I currently is a prime number. Let's output that prime number here, right? Let me remove this one. And let's output these, all of the prime numbers here. Now I just have to cancel out the multiples of this prime, right? So to do that, I would go like this. J is equal to 2 star I. J is less than equal to n and j plus equal to I. So it would start from 2i, then it would add an I into it, so it would become 3i, 4i, so on up until it is less than n, less than equal to n, and it would go over all of the multiples which are of I, which are less than equal to n, right? So for all those multiples, what I have to do is fj is equal to false. If they were false already, good enough. If they weren't, now they are false, right? So let me see if this code works. Again, let's just put 69. It's giving out the primes 2, 3, 5, 7, 11, 13 up until 67. Let me put 100. These are the primes. That's a very large number. Let me put a smaller number. So these are all the primes which are less than equal to 10 to the power 5. Right? We can also just output the number of primes which are less than equal to 10 to the power 5. Right? So let me come back to the slides. Right? So this was the code to find primes in all of 1 to n. The number of primes in 1 to n, well, you can calculate that from code as well. This number of primes in 1 to n is generally written as pi n. You can calculate pi n from code, but a lot of times you need this, an approximation of the number of primes in 1 to n to analyze whatever code you're writing, right? So the number of primes in 1 to n is around n by ln n. So pi n is around n by ln n, where ln is just log base e, right? So you can use this approximation to sometimes improve your code time analysis by a bit, right? The next point is same. The density of primes at some point n is big O of 1 by ln n. Of course, if there are the number of primes in 1 to n is n by ln n, the density of primes would be 1 by ln n, right? There are also 3 conjectures here which are not required much, right? I haven't really seen a lot of questions. Actually, I haven't seen any question requiring these conjectures. I have seen, actually that's a lie, I have seen one question on the, I think it was Project Euler. Yeah, I have seen one question on Project Euler which requires a legendary conjecture. But apart from Project Euler, I don't see these conjectures coming up in normal competitive programming contests. But still, you can see, you can just look at these conjectures from a mathematical point of view. The Goldbach conjecture says these conjectures are famous in mathematics. So it's good to know these conjectures even if these won't be required in competitive programming, right? So the Goldbach conjecture says n is equal to p1 plus p2, where p1 and p2 are prime for all n greater than 2. Basically, for all n greater than 2, you can write it as a sum of 2 prime numbers, right? Twin prime conjecture says we have an infinite number of prime pairs p comma p plus 2. Basically, no matter how far we go in the number line, let's say we are at the number 1000000000000, we can still find a prime bigger than this, who also has a prime, we can still find a prime which is bigger than this, p, where p plus 2 is also prime, right? This is called the twin prime conjecture, basically saying that we have an infinite number of prime pairs. This specific conjecture is very, very interesting. I found this very interesting when I was studying number theory, because there has been recent research done. Basically, there wasn't any kind of hope that we could prove this conjecture, right? This conjecture has been unproved for I don't know how long, like 300, 400 years, I don't know, maybe more than that. But recently in the 2000s, there has been research done which is close, which brings us closer to proving the twin prime conjecture. In that research, right, it wasn't exactly proving twin prime conjecture. In that research, what he did was, let me delete this one. Right, in that research, what he does was he proved that there are p plus 3, 6, 7. There were like 7 digits here, right? I do not remember the exact number, but there were 7 digits here. There are an infinite number of prime pairs like this, right? Where this can be less than equal to as well. So it can be p comma p plus 6 or p plus 10 or anything, right? So you can just search twin prime conjecture research right now to find that kind of knowledge as well, and I found that really interesting. You can find it interesting as well. Next, the legendary conjecture. There exists a prime between n square and n plus 1 square. This is also conjecture, basically stating that for all n, we can find a prime between n square and n plus 1 square. This conjecture specifically can be used to create computer programming questions. So, and I have seen a question of it on Project Euler. So it is kind of useful in some sense, but it is still very rare that you can just forget it. It doesn't matter. Right. Next, let's come on to the fundamental theorem of arithmetic. Before that, does any of you have any doubts? Kamal Pathak says root n will also work, right? Yeah, it will also work. In the Sieve of Eratosthenes code, right? Root n will also work, but you do not have to write root n, right? You can just go up unto n, because the time complexity would be same in both cases. Either you write root n or you write n. Basically, let me show what Kamal Pathak is asking, right? So in the Sieve of Eratosthenes code, we allowed I to go up until n, right? If we just allowed I to go up until square root of n and put I star I is less than or equal to n, this code would still work, right? Let me show you that this works. It stopped working. I shouldn't have stopped working. Oh yeah, we aren't going on the F5s later on, right? So let me go on the F5s later, that as well. Int I is equal to 2, I is less than or equal to n, I plus plus, if fi cout I. Right, this loop would still work, but the time complexity is still big of n log n, right? The time complexity hasn't changed, so it doesn't really matter if you put an I square, root n or normal n. Both of the loops, both of the implementation would have the same time complexity, so it doesn't really matter which one you pick, right? It's better to pick the normal one, because well, there is 2 characters less to write here. Let me go back to the slides. So the fundamental theorem of arithmetic says that for all n greater than 1, n is a product of unique set of primes, right? So what it says that we can write n as p1 to the power a1, p2 to the power a2 up until pk to the power ak for all n greater than 1, right? Example is 84. 84 can be written as 2 square into 3 to the power 1 into 10 to the power 1. What the term unique here says that this kind of configuration that we have here will not be equal to some n2 which is not equal to 84, right? We wouldn't have you know, simple set of primes have the product equal to one number and the second number as well. Basically, for two different numbers, we cannot have the same prime factorization, right? For each number, we have a unique prime factorization, and all of the prime factorizations do make up a number. We can have the same correspondence from the other side as well. No matter what P1, A1, P2, A2, etc. up until Pk, Ak we pick, right? We are just going to pick K pairs, and all of these P's should be primes, and A can be anything from 0 to infinity, right? No matter what kind of pairs we pick here, there would be an n corresponding to the product of them, right? So this is the fundamental theorem of arithmetic. This is really important in number theory. You most probably already know this, but with the use of this, we can calculate a different number of things, like the number of factors, which we denote as tau n, right? What will be the number of factors of n if n is p1 to the power a1, p2 to the power a2 up until pk to the power ak? It would be a1 plus 1, a2 plus 1, up until ak plus 1. How did it come out to be? Let me explain it. Right? So if we have a divisor d which is a factor of n, right? If d divides n and n is equal to p1 to the power a1, p2 to the power a2 up until pk to the power ak, then this divisor is of the form p1 to the power b1, p2 to the power b2, p3 to the power b3 up until pk to the power bk, where for every I, right, for every I between 0 and k, bi, right, bi is between 0 and ai, right? So each divisor of n would be of this form, which is p1 to the power b1, p2 to the power b2 up until pk to the power bk, and all of these bi's values, this is not pi, this is bi, sorry for my handwriting, this is bi to the power which are the exponents here, this is bi. Let me write this in a better way, right? And for all possible values of bi's here, right, there would be a corresponding factor d. What I want to say here, let me explain with an example. Right, here let us take the example 84. Example is 84, which is 2 square 3171, right? So a1, a2, a3 is 2 comma 1 comma 1 here, right? So what can we write as b1, b2, b3? There can be 3 into 2 into 2 possible sets of b1, b2, b3. How many tuples b1, b2, b3 we can have? There will be 3 into 2 into 2 sets of tuples, namely 0 comma 0 comma 0, 0 comma 0 comma 1, 0 comma 1 comma 0, 0 comma 1 comma 1, 1 comma 0 comma 0, 1 comma 0 comma 1, 1 comma 1 comma 0, 1 comma 1 comma 1, 2 comma 0 comma 0. Let me write this on a little bit more right hand side. 2 comma 0 comma 0, 2 comma 0 comma 1, 2 comma 1 comma 0, and 2 comma 1 comma 1. These are all of the possible b tuples that we can have, right, where each bi is less than equal to 0 and less than equal to ai, right? Corresponding to each b tuple that we have here, we would have a corresponding factor of 84. Corresponding to 0 0 0, what we will have here, 2 to the power 0, 3 to the power 0, 7 to the power 0, we would have 1. What we will have here, 7 to the power 1, which is 7. This would be 3, and this would be 2 to the power 0, 3 to the power 1, 7 to the power 1, which is 21. This would be 2, This would be 2 into 7, which is 14. This would be 2 into 3, which is 6. We would have 2 into 3, 6 into 7, which is 42. And all of these numbers like 1, 7, 3, 21, 2, 14, 6, 42, you can clearly see that all of these numbers are divisors of 84, right? Here we will have 2 square, 3 to the power 0, 7 to the power 0 as 4, which is also a divisor of 84. Here we would have 4 into 7, which is 28. Here we have 4 into 3, which is 12. And here we have 84, right? And we wouldn't have any divisors other than these numbers that we have written here. So the number of choices we have, for B1 we have A1 plus 1 choices. For B2 we have A2 plus 1 choices, right? For B1 we have A1 plus 1 choices. For B3 we have A3 plus 1 choices. Multiplying them all together, we get the number of factors, which is tau n, A1 plus 1, A2 plus 1 up until AK plus 1, right? Similarly, we can calculate the sum of factors and the product of factors as well. Let me show you these two very quick as well. So to calculate the sum of factors, what we are doing is just calculating P1 to the power 0, P2 to the power 0 up until Pk to the power 0, plus P1 to the power 0, P2 to the power 0 up until Pk to the power 1, plus so on up until P1 to the power 0, P2 to the power 0, Pk to the power Ak, right? Then we go on to the next kind of set, which should be P1 to the power 0, P2 to the power 0 up until Pk minus 1 to the power 1 and Pk 0. Basically we are moving on like in a regular number system, right? So the sum of all these kind of factors would be the sum of factors, right, as I've written here. But here you might be able to see that all of these terms up until this term, right, are equal. All of these terms are P1 to the power 0, P to the power 0 up until Pk minus 1 to the power 0. Next we would have P1 to the power 0, P2 to the power 0 up until Pk to the power Pk minus 1 to the power 1, and then we would have Pk varying from 0 up until Ak, right? Next we would have Pk minus 1 to the power 2, and again we would have Pk varying from 0 to Ak, and so on, right? So we can take common like this. We can basically apply distributive property, and we get P1 to the power 0, P2 to the power 0, etc. Pk to the power 0 plus Pk to the power 1, etc. up until Pk to the power Ak, right? Plus we take the next number, which is this one, right? P1 to the power 0 up until Pk minus 1 to the power 1, and we get the same term which we had here, right? And so on. Next we can again take the common for Pk minus 1, and we would get P1 to the power 0, P to the power 0. This time we are taking the terms from here to here, right? We are taking the terms from here to here up until Pk minus 1, and we are taking this as a common term. In that, when we do that, what we will get P1 to the power 0, P2 to the power 0 up until Pk minus 1 to the power 0, Pk minus 1 plus, sorry, here would be a plus, to the power 1, etc. Pk minus 1 to the power Ak minus 1 into Pk to the power 0 plus Pk to the power 1 up until Pk to the power Ak. If you are following what I'm saying here, you can clearly see that basically for every power term, we can replace it with in the sum of factors form. We can replace it with a term like this, right? So we will start with P0 to the power 0, P plus. Sorry about that. Let me erase this. Right. So sum of factors would be P1 to the power 0 plus P1 to the power 1 up until P1 to the power A1 into P2 to the power 0 plus P2 to the power 1 up until P2 to the power A2, going like this up until Pk to the power 0 plus Pk to to the power 1 up until pk to the power ak. We can reduce a single term like this as well, p1 to the power 0 plus p1 to the power 1 up until p1 to the power a1. If we see it as a geometric progression and apply the geometric progression formula, we get p1 to the power a1 plus 1 minus 1 by p1 minus 1, right? So the sum of factors here is just product of the sum of factors here is just a product of I is equal to 1 to k pi to the power ai plus 1 minus 1 by pi minus 1, right? If we take the product of all k values like this, we get the sum of factors, which is this one. Product of factors is n to the power tau n by 2, right? You can clearly this how this works as well. Basically you do the same thing that we did here, right? You take each form and instead of adding them, you multiply them, and you will easily see that right, we get the form n to the power tau n by 2. Next, I will go on to the YouTube chat to see the doubts. Before that, let me give you a question. What is the number of perfect squares which are divisors of n, right? So basically, I want to find all of the divisors n, divisors d of n, such that d is a perfect square, right? D is x square, where x is an integer. How many d's of this sort exist, right? N is this term, right? p1 to the power a1, p2 to the power t2 upon pk to the power ak. You assume n is that, and then what would be the number of perfect squares, divisors of n, from a, b, c, d. Just write a, b, c, or d in chat. Up until then, let me see if there are any doubts. Deepak Sharma says, hello sir, can I continue from here or need to go through from the beginning in order to get this whole? You can continue from here. I'm explaining very simple things, so I don't think you need to go from the beginning to understand again. You know, if you get confused at some point, then it's would be better if you start from beginning, but up until you are not getting confused, it's all right. Kamal Pathak says C. Any other answers? Maharshi Vishnu Chavda says, can you please explain expression of the sum of factors? Yeah, I admit that I kind of rushed that one, because the actual way in which you calculate the sum of factors, right, is through induction, right? Actually, let me go on to the sum of factors term once again. Can you please explain final expression of the sum of factors? Alright, let me go on to that. Right, this is a final expression of the sum of factors. Let me put it on a new slide. Right, so the final form of the sum of factors is product of I is equal to 1 to k pi to the power ai plus 1 minus 1 by pi minus 1. Right, this term is just the geometric summation formula, right? If you have a geometric series and you add that geometric series with itself, what is the summation formula? It's this formula. If you write the corresponding geometric series corresponding to this term, it would be like this: pi to the power 0 plus pi to the power 1 up until pi to the power ai. Right? So basically, we are multiplying this kind of term for all I. We're multiplying this with pi plus 1 to the power 0, but pi plus 1 to the power 1 up until pi plus 1 to the power ai plus 1, right, and so on in the left hand side as well, from 1 to k. Right, by doing so you can kind of expand this whole you know, product as well. You have k products here, right? Let me write it in a smaller format. Let's write p1 to the power 0 plus p1 to the power 1 plus p1 square, and I'm multiplying this with p2 to the power 0 plus p2 to the power 1. This is an example that I'm giving you. Let's say there is a number which only has 2 primes. n is equal to p1 square into p2 to the power 1, it would have 6 factors, right? And those 6 factors would be p1 to the power 0, p2 to the power 0, plus p1 to the power 1, p2 to the power 0, plus p1 square, p2 to the power 0, plus p1 to the power 0, p2 to the power 1, plus p1 to the power 1, p2 to the power 1, plus p1 square, p2 to the power 1, right? So in a sense, expanding this whole thing would give us all of the factors of n here, and we are just summing them up. The actual proof involves induction. So all of the things that I explained here were just to give you an intuition of why it's happening. I understood it through this intuition. If you want to know the actual proof you can derive on yourself as well. It's not that difficult. But if you want to know it, you can just search the sum of factors expression and its proof. I think the answer is C, Devang Bhagat. Yes, Devang Bhagat, you are correct. Kumar Patak, you are correct as well. The answer here is indeed C, right? This is because in a perfect square, right? In a perfect square, you'll notice, right? This is an expression of a perfect square. D is equal to x square. Let's take x is equal to p1 to the power a1 up until pk to the power ak. If this is our x, and we are squaring it to get d, what will happen is we just multiply this 2 with everything. So d, which is x square, would be p1 2a1, p2 to the power 2a2, so on, pk to the power 2ak, basically saying that every prime in d would have an even power, right? Every prime in d has an even power, and if every prime in D has an even power, then D is a perfect square, right? So to get the number of perfect squares in the divisors of n, what we do is, let's say n is p1 to the power a1. Here a1, a2 are anything, not to be confused by the a1, a2 I took in this x, right? These are new a1, a2s and p1, p2s, right? We take these numbers. The divisors which are a perfect square, what powers would it have for p1? It can have p1 to the power 0 or p1 square or p1 to the power 4 or up until p1 into 2 into a1 by 2 ka floor, right? We can multiply this with p2 to the power 0 or p2 square or everything. So how many choices do we have here? We have a1 by 2 plus 1 choices. Similarly for p2, similarly for p3, etc. up until pk. Any number that we multiply from here, let's say we choose p1 to the power 4 here, we choose p2 square here, we choose something here, we choose something here. Whatever we multiply, all of its prime powers would be even, and hence it would have a square root, right? So the total number of choices multiplied we have is a1 by 2 floor plus 1, a2 by 2 plus 4 plus 1, and so this is the number of perfect square divisors of n, right? Let us move on to factorization. Now factorization is just the code is just the method to write n as a product of its prime powers. Basically, if you're given an n in a function, you want to output p1, a1, p2, a2, and so on up until pk, ak. You want to output all of these numbers, right? How do you do that? That method is called factorization. The code or the kind of algorithms that reduce this n to p1, a1, p2, a2, and etc. up until pk, ak are called factorization algorithms. There are a lot of research being done in factorization algorithms because it is required in cryptology. Cryptonomy. Is it cryptonomy or cryptology? It's whatever, right? It is required in that, and it's required in various other fields of computer science as well. So there is a lot of research being done here, right? The naive algorithm to factorize a number can be done in big of root n, just like to find a prime, just to find if a number is prime or not, we can apply the same kind of a loop to factorize a number in big of root n, right? But there is a very good algorithm as well. This is not the best algorithm, but this is a very good algorithm that is sometimes required in competitive programming. That is sometimes required in competitive programming contests. This algorithm is known as Pollard row, and its complexity is big of n to the power 1 by 4, right? This is fourth root of n, right? Or n to the power 1 by 4 into log n. This is known as Pollard row factorization. Pollard row factorization. And if you want to read about this, you can do so. I will not be teaching this during this lecture, but you can absolutely search Pollard row factorization and get to know about how we factorize a number very efficiently. To do multiple queries, if you're given multiple queries and you want to, let's say you're given n1, n2 up until nq, right? And you want to find the factorization of all of these numbers. Or this kind of subtask appears in your code where you have to very efficiently find the factorization of different numbers and want to output something on it. Then you have to modify your sieve a little bit, and with that modification of sieve, you can then once you apply the sieve of n log n, where n is the maximum n that will appear here, the maximum n that will appear here, you say that as n, right? And then you can answer each query, which is each factorization, in log n time. Once you run your sieve, and then each factorization would take log n time, right? So this is the total complexity, which is n log n plus q log n, right? Let me explain both of these algorithms, the single query algorithm and the multiple queries algorithm in code, right? These are just going to be slight modifications of the primality test. So let me just switch to my code editor. I think you will be able to understand through code itself, right? So we want to output the factorization for n, right? One question that you should ask: how are we going to store this factorization, right? So you can store it in different data structures. You can store it in a vector of int, right, where you will store let's say you want to store factorization of 12 there, right? Then your v would contain 2 comma 2 comma 3, because 2 into 2 into 3 is 12, right? So you can store it in a vector like this, but right now I'm going to have a map int comma int, where if you want to store the same thing, the factorization of 12, you would store the prime power pair in this map, right? So you would store for 2, 2, which is 2 square, and for 3 you would store 1, right? So 2 to the power 2 into 3 to the power 1 is 12, right? So remove this. For I is equal to 2, I star I less than equal to n, I plus plus, what you have to do here, right, is just do this. While n modulo I is equal to 0, right? While n is dividing I, up until it is doing that, what you do is you put vi plus plus first of all, because we have additional power of I in our n, right? If I has not been initialized, if vi has not been initialized, then vi would be initialized automatically to 0, and it will get to 1 with this piece of code, right? And then you divide n by I, right? So if you want to see what will happen in the case of, let's say, 16 into 3, what is 16 into 3? 48, right? So if you want to see what would happen in the case of 48, it will get to 2, right? So it will first run for 48, right? We would have v2 is equal to 1, right? 48 modulo 2 is equal to 0, right? So it would go into this loop. It would set v2 is equal to 1, and then it would set n is equal to 24. Then it would go again here. 24 modulo 2 is equal to 0 as well. It would set v2 is equal to 2, and it would set n is equal to 12 here. Going on like this, it would set 10 modulo 2 is equal to 0. It would set v2 is equal to 3, and it would set n is equal to 6. Again, it would go into this loop, it would set v2 is equal to 4 and n would be 3 now, right? And now when n is 3, you see this loop would automatically terminate. Why would it terminate? Because this inner loop has been completed, right? It would just go to this outer loop, right? And in this outer loop now I is equal to 3, right? And as you can see, not 3, 3 star 3 is equal to 9, which is greater than n, right? N was 48 before, this was n which was 48 before, but now n has the value of 3, and so this loop would terminate with n is equal to 3, right? And we would just have the values v2 is equal to 4 inside. We would not have v3 is equal to 1. So we have to take care of that as well outside of this loop. If n is greater than 1, vn plus plus n is equal to 1, right? So let us output this map for auto it in map cout it dot first it dot second, right? Let us output it in such a manner, and let me remove this output. There was some kind of error. Acha, it would be a v here. Let's put 100. It would be 2 square into 5 square. Let's put 69. That would be 3 to the power into 23 to the power 1. Let me put something big. It's a prime number. Let me put another big number. It's a product of two primes. Let me put 9. Let me put 9. It's 3 to the power 4 into 37 to the power 1 into 33667. Let me put something else. Let me put 1728. That's 2 to the power 6 into 3 to the power 3, right? So it is working. Next, let me show you the code that we are. How are we going to modify the Sieve algorithm to basically work to basically include factorization as well. So let me comment this all out, right? Here, what we are going to do in the Sieve algorithm that we had, we were just storing the Boolean value, that is this number a prime or not. Now we are going to be storing one additional number with every corresponding to every integer, and this value would be lowest prime factor n plus 1, right? So for each number from 1 to n, we are going to be storing the lowest prime factor n has as well, right? We do not have to store it for f0 and f1. Actually, let me first do this, right? Here we can actually remove bool n plus 1, right? Instead of keeping bool n plus 1, we can just make do with lowest prime factor as well. Initially, we would keep the lowest prime factor's value of all I as I. If the lowest prime factor of I is equal to I, then that means I is I, right? I is prime, right? So we do not have to we do not have to keep an additional Boolean array of f as well, right? We would remove lowest prime factor of 0 and lowest prime factor of 1 as 0, or let's just put it as -1. We can put it as anything, right? And now if fi, instead of writing fi, which was 2 before, we would write if lowest prime factor of I is equal to I, then that means I is prime. And then only we would go into the internal loop. And in the internal loop, what we are going to write is if a lowest prime factor of j is equal to j, only then we would modify the lowest prime factor here, right? If the lowest prime factor has already been changed, then we do not want to change it again, right? Because let's say 6, right? We have already set the lowest prime factor of 6 as 2. But in the iteration level, when I is equal to 3, we would go on to 6, right? Because 6 is a multiple of 3. But we do not want to change the lowest prime factor of 6. Again, we do not want to set it to 3 because that is not the lowest prime factor of 6, that is equal to 2. So we would only change the lowest prime factor of j when j is currently presumed to be a prime number, and in that case we would set lowest prime factor of j is equal to I. Now if we want to factorize a number, right, let's take in some queries int q, c, and q, and for q minus minus we are taking in some additional numbers x, c, and x, right, and we are storing their factorization in a map called map, right, and we want to basically factorize x and store the factorization map in the map. How do we do that? We do this by a simple loop like this: while x is greater than 1, map of lowest prime factor of x plus plus and x by equal to lowest prime factor of x. Finally, we will just output the values of map to see if our code is working correctly or not. Right? I think this should work. There is an error in the code, but I don't think that is an actual error. It is an error. Oh, it's a while loop. Right, it works. So let us see if this is working or not. Let's first keep n, the maximum limit up until which we have to calculate numbers, as large. So we'll keep it as 10 to the power 6. This is 10 to the power 6, right? Yeah. The sieve would easily work up until then. I guess not. Let's put it as 10 to the power 5. If we had put a static array or a vector, then it would have worked, but because C++ does not allow large arrays to be built in the stack, it wasn't building before. But anyways, now as we have kept 10 to the power 5, we can put our queries. Let's put 10 queries here. So 1728, that's giving 2 to the power 6 into 3 to the power 3, 9999, 2 into 4 into 5 into 7, that's 28. No, that's not 28. 2 into 3 is 6, 6 into 5 is 30, 210, 2 into 5 into 7, and 420, 420, 1337, and so on. Yeah, so it's giving the factorization of each number in just big of log n time. You can understand why it's giving it in big of log n time through this loop, because the lowest prime factor of each x greater than 1 would at least be 2, right? And at each step we are dividing x by the lowest prime factor. So at each step it would at least get halved, and if it's getting halved at each point, we would only require log n steps here, only log x steps, right? So this is the loop to this is the code to factorize multiple numbers efficiently by applying a Sieve of Eratosthenes before. Did every one of you got it? Harshapati says ours. Thank you. So if you have any doubts with this code, just let me know. Up until then, I will go on to the next part, which is Euclid's GCD algorithm. Right? We have only 35 minutes in. I'm for sure going to be extending this class. So it's more going to be a class of around, I think, 2.5 hours. So I'm still going. This session has 1 hour remaining. Right, up in the session I'm going to be covering Euclid's GCD. The only topics remaining are Euclid's GCD algorithm and modular arithmetic, the two main kind of topics remaining. Modular arithmetic is very big, but I will try to cover it. Right, so let us come on to Euclid's GCD algorithm first. Right, so what is Euclid's GCD algorithm? As we have seen before, in factorization, we do not have very efficient algorithms, right? We have big of root n algorithms, we have big of n to the power 4 log n algorithms, but we do not have any log n kind of algorithm that we have in primality tests, right? Uh, so factorization is kind of a very powerful tool, and to use this powerful tool, which is factorization, we have to use powerful algorithms. But there is a simpler tool, right? There is a comparatively simpler tool than factorization, but it is still very powerful that we can use to aid in our questions, and the time complexity there is very less than the time complexities of factorization, which is GCD, right? GCD, as you many of you might remember, GCD of a comma b is the largest n, is the largest possible d, is the largest possible d, such that d divides a and d divides b, right? GCD, which is the greatest common divisor of a and b, is the greatest common divisor of b, right? There is not much really to explain here. D is just the largest number which divides a and divides b. The common divisors of a and b are all of the numbers which divides a and divides b as well. The largest of those numbers is considered as GCD a comma b, right? So Euclid's GCD algorithm is an algorithm to find the GCD of some a and b, right? What it says is, for any GCD a comma b of Euclid's GCD theorem, what does Euclid's GCD theorem says? It says GCD a comma b is equal to GCD of b comma a mod b. Here I'm assuming a is greater than b, but it would work for b greater than a as well. So for some a greater than b, GCD a comma b is equal to GCD b comma a mod b. And this, if you write this in a recurrence kind of form, where you have a function which is the GCD here, right, and you have two numbers int a comma b, right? If you have two numbers in a function like GCD and you just return GCD of b comma a mod b, then the terminating step there would be GCD a comma 0 is equal to 0. Sorry, not 0, it should be a here. Right? GCD a comma 0 is equal to a. So GCD we consider all of the numbers to be a factor of 0, right? We considered any x to be a factor of 0. So that is why GCD a comma 0 is equal to a. Right? And this would be the terminating step in your GCD algorithm. The complexity, if you write this recursive function, is big O of log of minimum a comma b. I'll explain how this complexity comes out to be, but first let me show you the code for this. Right, the code would be very easy, as you would expect. Let me actually remove all of this first, right? And let us just take two numbers a and b, right? And we will just output the GCD of a comma b here, right? So int GCD of int a comma int b is just return GCD of b comma a modulo b, and if b equal to 0, then we have to return a. This would work. Let us test if this is working. Let me take two numbers, 191 and 382. The GCD is 191. I don't know why it took these two numbers, but let me take some other numbers, 10 16, 13 5, 1, and so it's working, right? If you want to see it what's happening here in a more better way, so that you can understand intuitively what's happening, let me come back to the slides, right? Hello. Okay, so I'm back online. I didn't know what happened. I was teaching like I normally do. At one point of time, I guess OBS just decided to stop on itself. So I think I was explaining the Euclid's GCD algorithm when the stream ended. At least that's what it looked like to me, right? So I'll just continue from that point on. So I'm sorry about the inconvenience about the stream ending on its own. I'm not sure why it happened. But anyways, let's come back to the Euclid's GCD algorithm, right? In here, we were talking about, let me go back to the slides, right? I showed the complexity. The complexity here is going to be big of log min of a comma b, right? Uh, let's go on to the extended Euclid's algorithm, right? So what happens in extended Euclid algorithm? Here we are trying to compute some x and y such that xa plus yb is equal to GCD of a comma b, right? There would exist some x and y where x and y are integers. We of course trying to compute some integers here, right? So of course some x and y integers would exist where x a plus y b is equal to GCD a comma b. In fact, GCD a comma b has another definition, right? GCD a comma b is the smallest positive value of xa plus yb, right? Smallest possible value, smallest positive value of xa plus yb where x and y are integers is equal to GCD a comma b, right? But what are those x and y? To calculate that, we are just going to be modifying our Euclid's GCD algorithm by a little bit. Basically, here, what we did here, of course, at the last step, the x and y are going to be 1 and 0 or 1 and k, right? I'm just going to be writing 0 here, but you can of course write any k here, any integer here, right? Because any integer multiplied by 0 is 0, right? This also allows us for some degree of freedom in choosing our x and y, but I'm just going to be taking 0 here for right now, right? And then what it does, right? It if we have x1 b plus y1 a modulo b is equal to GCD of a comma b, then we can write y1 a plus x1 minus y1 a by b floor b is equal to GCD a comma b. What did I just say? So let me explain that more properly. So this is the lower level that we have, right? We were recurrence down by calling GCD a comma b. To calculate GCD a comma b, we were calling GCD b comma a mod b, right? That function returns us x1 and y1. These x1 and y1 are returned by this function, which is GCD b comma a mod b, right? Where x1 b plus y1 a mod b is equal to GCD a comma b. Using these x1 and y1, we can calculate the next x2 and y2, where x2a plus y2b is equal to GCD. How do we do that? Let me show that, right? So we have x1 into b plus y1 into a modulo b is equal to GCD, right? So I'm going to be writing this remainder of this division in another form, right? This is a is equal to bq plus r. This is the r term from a is equal to bq plus r, right? So a minus bq is equal to r, right? So instead of writing this r here, I'm going to be writing a minus bq. So x1b plus y1, this is going to be transformed like this. A minus b into what is q? A by b floor is equal to GCD. Just expanding this brackets here, we get x1b plus y1a minus y1 a by b floor into b is equal to GCD. Taking common with b and a, we get y1a on the left hand side plus x1 minus y1 a by b floor into b on the right hand side, right? So these are the x2 and y2 that we want, right? To show this in code, first let me show this in an example, right? So we had 1 and 0 here. We are going to be replacing them with y1 and x1 minus y1 a comma b, right? So this y1 that we have on the right hand side will come up on the left hand side automatically. So y1 is 0 here, so we get a 0 into 4 multiplied here, plus we get x1 minus y1 into a by b. Y1 is 0, so anything multiplied by that is 0. We get a 1 here automatically, right? Then this 1 would come up here automatically, and this would become 0 minus 6 by 4. 6 by 4 is 1. 6 by 4 is 1 into 1, right? So 1 into 1 is 1. So this is just 6 minus 4 is equal to 2, right? We get this minus 1 here automatically, and next we compute 1 minus 10 by 6 into minus 1, which is 1 minus minus 1, which is 2. So we write a 2 here. So 10 plus minus 10 plus 12 is equal to 2. That is correct as well. We get this 2 automatically from the left hand side, and calculating the last number, that is 2 minus, sorry, not 2, this would be a minus 1 here, minus 1 minus 2 into 16 by 10 ka floor, which is minus 3, right? So 2 into 16, which is 32, minus 30 is equal to 2, so this one is correct as well. So we got the numbers 2 comma minus 3 from here. To show this in code, let me show my code editor. Instead of returning an int here, what are we going to be returning? A pair of int comma int. If b is equal to 0, then we are going to be returning 1 comma 0, because a into b, a into 1 plus b into 0 would get us our GCD. Else, what are we going to do is, first of all, we are going to be taking these numbers in a new format. T is equal to GCD of b comma a model b. Here, what are we going to return? A pair of t dot second comma t dot first minus t dot second into a by b, and this will work, right? Here we can output GCD a comma b dot first and GCD a comma b dot second. Let us see if this works. Then we put 2 random numbers in here. Let me put 1000 and 1337. Their GCD I assume would be 1, and if we multiply 1000 by minus 365 and 1337 with 273, we would get the correct answer. Let me actually see if this is correct. 1000 into minus 365 plus 1337 into 273, that is 1. So this is working as well. Right. Okay. So this extended GCD algorithm is this to calculate the x and y terms which result in the d GCD term, right? And this is working as well. Let me come back to the Euclid GCD algorithm. Now, why is extended Euclid algorithm is needed? The GCD algorithm might be needed a lot, right? It is actually needed a lot. The GCD algorithm is like crucial to number theory concepts because it's just so it's just so efficient, right? Because the GCD algorithm is so efficient, it is sometimes used where a factorization would easily do the trick, right? When you have an algorithm where the factorization would easily do the trick, you have to think, how can I do this without factorization and by just using the Euclid GCD algorithm, because the GCD algorithm is faster, right? So GCD algorithm is really crucial. But why is extended Euclid algorithm crucial? Because there are a lot of questions in computer programming which appear like this, where you have to solve linear Diophantine equations. So what are linear Diophantine equations? It's just a fancy name to say that we have to calculate xa plus yb is equal to c, where we are given a, b and c, right? We are given a, b and c, and we want to find x and y such that xa plus yb is equal to c. So this is only possible when GCD of a comma b divides c, right? If it doesn't divide C, if GCD A comma B is, let's say GCD of A comma B is 5 and C is 4 or 9, anything, where any number which isn't divisible by 5, then we cannot find such x and y such that xa plus yb is equal to c. It has no solutions. But when GCD A comma B is divisible by C, we can use the extended GCD algorithm to find x naught and y naught, x naught y naught b, such that x naught a plus y naught b is equal to GCD A comma B, right? We can multiply this equation on left hand side and right hand side by C by GCD, right? C by GCD, and we can get C on the right hand side, and on the left hand side we get x naught into C by GCD and y naught C by GCD. This is not the only solution. There will be multiple solutions, but we can get a particular solution like this. You can then use this solution to compute the other solutions, right? Similarly, we can have linear Diophantine equations of more than two variables as well, like this one right here. X a plus y b plus z c is equal to d. This is another linear Diophantine equation. And to solve this kind of equation, what you do is you first solve this equation, right? What you basically do is you write xa plus yb as sum w into e, right? Where e is GCD of a comma b, right? And w is just any number that we are picking up, right? W is some integer, and e is equal to GCD of a comma b, right? As e is equal to GCD a comma b, we can write it as x naught a plus y naught b as well. We multiply that by w, we get w x naught a plus w y naught b plus z c is equal to d. We want to compute this, right? Basically we want to compute such w and z such that this equation satisfies. We want to calculate w e plus z c is equal to d. This is again a two-dimensional linear Diophantine equation in two variables, right? So you can easily solve that. You can easily solve this similarly how you solve this one, right? Where you take e and c as constant and you have to compute these two numbers, right? So basically what you do is you factor out two numbers and turn it into a single number, which is the GCD of a and b, and then you are multiplying with another number. This is how you solve linear Diophantine equations containing more than two variables, right? So if there are any doubts right now, I don't think there would be a lot of participation left, as there was a connection trouble in the middle of the class. But if you have any doubts, I'm going to be solving them in a bit. Before that, let me give you a question. Here, solve for x and y in 13x plus 8y is equal to 7. Which of these options are correct? A, B, C, and D. You can just write whichever option is correct in the chat. So are there any doubts right now? Sorry Maharshi, Vishnu and LG for the abrupt ending of the stream. OBS just decided to just close at some point. Actually, let me solve this question directly, right? So let me solve this question here, right? Here we are going to be applying the extended GCD algorithm, right? So we have 13 and 8, right? 13 and 8. What will be the GCD? To calculate the GCD, we are going to be calling in the Euclid GCD algorithm. So 13, 8, we get 8, 5, because 13 modulo 8 is 5. Then we get 5 and 3 because 8 modulo 5 is 3. Then we get 3 and 2 because 5 modulo 3 is 2. Then we get 2 and 1 because 3 modulo 2 is 1. And then we get a 1 and a 0, right? So the GCD of these two numbers, 13 and 8, is 1, right? Now we can calculate the x and y's for this. So let's put a 1 here and let's put a 0 here, right? This is equal to 1. This will also be equal to 1. This will also be equal to 1. This will also be equal to 1, right? So we get a plus sign between them. And let's just apply the extended GCD algorithm. So this 0 would directly come on the left hand side, and this would be this would directly become as a 1. Then this would directly come as a 1 here, and we would get a minus 1 here automatically. Then we would get a minus 1 here, and we would get a 2 here. Then we get the 2 here automatically, and then we get minus 1 minus 2 on the right hand side, so a minus 3 here, because 16 minus 15 is 1. Yes, that's correct. And then we get a minus 3 here and a 5 here, right? So the answers are minus 3 and 5. Is minus 3 and 5 here? Yes, but this is not the correct answer, because minus 3 into 13 plus 5 into 8 is equal to 1, not 7, right? So to get the answers for 7, we have to multiply these values by 7, which are minus 3 and 5. If you multiply them by 7, we get minus 21 and 35, right? So is that in the options? Yes. So that is the correct answer. What about the other two options? These two options are also correct, but we just solved the extended GCD algorithm and we got a solution, and we multiplied them by 7, we got minus 21 and 35. How are these options correct? Because whatever answers you get from here, right, whatever options you get from here, let's call them as x naught into a plus y naught into b is equal to some c, right? You can add into x naught some multiple of b by GCD of a comma b, right? And you can subtract from y naught, some multiple, the same multiple which you added here, the same multiple you have to subtract from here as well, into a by GCD a comma b into b. That is also actually equal to c. Why so? Because if you expand this expression right here, if you expand this expression, you get x naught into a plus y naught into b, that is equal to c, and these two terms cancel out with each other, because these two terms a b, these two terms are equivalent to k into a b by GCD a comma b, right? So here, what is this and what is this that we can add and subtract to the minus 21 and 35? B comma GCD a comma b, that is 8 by 1, which is 8. We can add some multiple of 8 to minus 21. This multiple can be negative as well, but yeah, this k can be negative or positive, anything that you want. And a by GCD, GCD is 1, so, and a is 13, so we can subtract k 13 here, right? Keeping k as 3, we get 3 and minus 4, so this option is correct as well. And keeping k as 2, we get minus 5 and 9, so this option is correct as well. This is 13, not 15, right? So if you have any doubt in this particular example, do let me know. If not, I will go on to modular arithmetic, which is the largest topic today, right? So we are going to be covering modular arithmetic now, and then I'm going to be calling this class an end. So are there any doubts? I guess not. So let me move on to modular arithmetic, right? What does modular arithmetic mean? Arithmetic that we do in a modular context, right? So let's say we want to calculate a plus b modulo m, right? Here modulo m is the same operation that I showed you in the division in the first slide, which is the remainder when we divide a by b, right? So a plus b modulo m is equal to a modulo m plus b modulo m mod m, right? This is one property of modular arithmetic. When we the remainder that we get after adding two numbers and dividing by m is equal to the remainder of the first number by after dividing by m plus the remainder of the second number divided by m, and the number that we get, if we get the remainder of 8 modulo m, that is the same as the remainder of the sum modulo m, right? And why is this property useful? Well, because this helps us in avoiding overflow in our code. Let's say we want to add some numbers, right, xi's from I is equal to 1 to 10 to the power 5, and each xi is of the order 10 to the power 9, right? And we are summing this up in an int format, right? So 10 to the power 9 into 10 to the power 5, this is the largest number that we can, this is the largest sum that we can get here, right? That is equal to 10 to the power 14, which is greater than or equal to 2 into 10 to the power 9, right? That is greater than 2 into 10 to the power 9, which is the int limit. So of course this will overflow, right? Instead, what you do, if you want to calculate this modulo sum m, where m is around 10 to the power 9, what you do is you first add x1 and x2 and take its modulo m. Then add x3 to it, take modulo m of it as well, and so on. You keep doing that. You will never encounter any integer overflow during this entire process, because any every number here would be less than m, right? And any number which is less than 10 to the power 9 plus any number which is less than 10 to the power 9 would give us a number which is less than 2 into 10 to the power 9, which is less than the int limit, right? Similarly, we have the second property of modular arithmetic is as well, corresponding to subtraction. A minus b mod m is a mod m minus b mod m mod m. In code, always check if the result is negative. Of course, here it can happen that the result is coming out to be negative, right? So in C++, in mathematics, we want the result to be positive, right? Because mod m always results positive in normal mathematics. It's just that in C++ it might return negative, right? So to transform that value from negative to positive, what we do, wait a second. What we do is we add a plus m here, right? By adding a plus m here, b minus b modulo m, right? This b modulo m is going to be less than or equal to m, right? This b modulo m is going to be less than m. So minus b mod m is going to be greater than minus m, and if we add an m there, right, this is going to be greater than 0. M minus b mod m is greater than 0, right? So we can just add an m there and the result would always be positive. A b mod m is a mod m into b mod m, right? Of course, if m is around 10 to the power 9, you have to perform this multiplication internally in long format, because a mod m would be of the order 10 to the power 9, b mod m would also be of order 10 to the power 9. Multiplying that, we get a number of order 10 to the power 18, and this would not fit in the int format, so you have to use a long format, right? Also, if m is the order of 10 to the power 18, then you have to use int 128 to multiply, right? You have to get to the next big integer data type, which is underscore int 128. This is only available in 64-bit machines, so I don't think it would be available in CodeChef, but it is certainly available on Codeforces, right? So this is modular arithmetic for addition, subtraction, and multiplication. But what about exponentiation and what about division, right? So we are going to be discussing these two questions next. So let us first come to modular exponentiation, right? We want to calculate a to the power b mod m. You can of course do so in a naive format by taking an answer as 1, right? And then for int I is equal to 1 to b, right? What you do, if you want to calculate a to the power b, right? For I is equal to 1 to b, what you do is answer is equal to, of course we want to multiply in long format, so 1 ll into answer into a mod m, right? You do this for b times, you get a to the power b. Simple enough, but this is going to take a time complexity of big O b, right? So to improve that, we can use modular exponentiation code, which is similar to binary exponentiation which you might have seen before, right? This takes big O of log b time. This also goes by the name of repeated squaring paradigm. So what you are doing is, basically, if b is even, you are breaking a to the power b mod m as a to the power b by 2 into a to the power b by 2 mod m, right? So here you only have to calculate this number. Basically, if this is a function call, let's call this as a function call of a comma b comma m, then you have to call a comma b by 2 comma m and just multiply that with the same value that you get here. You only have to calculate this number once, let's say t, and then you just return t into t modulo m, right? If b is odd, you do a similar thing. A b is equal to a b by 2 floor into a b by 2 floor into a mod m, right? So here as well, you only have to calculate this number, which let's say is t. You multiply t by t and a, you get the answer, right? So of course, at each step, our b is getting halved, at least halved. At each step, b is getting halved, right? And the terminating step would be when b is equal to 0 or b is equal to 1. Those would be the terminating steps. So what is the time complexity here? The time complexity would be simple, big O of log b, right? But what if, first let us see this code in action, not code, algorithm in action. So let's say if you want to calculate 5 to the power 4 modulo 13 or 12 would be better, right? If we want to calculate 5 to the power 12 modulo 13. So how do we do that? To calculate 5 to the power 12 modulo 13, we are going to be calculating 5 to the power 6 modulo 13 first. To calculate that, we as 6 is even, we are going to be calculating 5 to the power 3 modulo 13 first. To calculate 5 to the power 3, as 3 is odd, 3 by 2 is 1.5 and 1.5 floor is 1. We are going to be calculating 5 to the power 1 modulo 13. Let's call this as a terminating step. We can go further beyond, but let's call this as a terminating step. This will return 5, as 5 to the power 1 is 5. So to calculate this, we will multiply 5 by 5 by 5, which would be 125. 125 modulo 13 is, we can actually do it in a better way. 5 into 5 modulo 13 into 5 modulo 13. Let's do it in this fashion, right? 5 into 5 is 25, and 25 modulo 13 is 12, right? So instead of 12, I can write a minus 1. Minus 1 into 5 modulo 13. So minus 1 into 5 is minus 5 modulo 13, and minus 5 modulo 13 is just 8. So this would be 8, because 8 minus 5 is 13 minus 5 is 8, right? So yeah, this value is 8. So let's calculate 5 to the power 6 using 5 to the power 3, which would be just 8 into 8 modulo 13, and this would actually be equal to 5 into 5, because we are just multiplying minus 5 into minus 5, right? So these minus and minus get cancel out. 5 into 5 is 25, and 25 modulo 13 is 12, right? Or minus 1. So 5 to the power 6 modulo 13 is 12, and so if we apply that here, what is 12 into 12 modulo 13? You can of course try to calculate 144 modulo 13, but 12 is minus 1 here. You can also put 12 as minus 1. Minus 1 multiplied by minus 1, minus gets cancelled out. This would just be 1. So 5 to the power 12 modulo 13 is 1. Right? So, but there is one thing that we still can't do, right? The one thing that we still can't do, if you're given 3 numbers, let's say a, b and c, you want to calculate a to the power b to the power c. How would you do that? Right? Modulo m. Let's say you're given another number m. You want to calculate this modulo m, right? Of course, you can do this by first calculating b to the power c. You calculate b to the power c normally, right? Without modulo m, right? And then you keep that, let's say you get t here, and then you calculate a to the power t modulo m. This would take a time complexity of log t. And what is log t? Big O of log t. And log t, as can be seen from here, big O of log t is just big O of c, right? So the time complexity directly depends on c here. Actually, b to the power c would be very large as well, so the time complexity would actually be larger than this, but let's just keep it as big of c now. It's still linear, right? We still have to apply a lot of steps in this c direction, which you do not want to. Can we calculate b to the power c modulo m, right? If we can calculate b to the power c modulo m, then that would help us. Then this number would not be so big. This log t is coming out to be big of c because t is very big, right? B to the power c can be very big. We do not want b to the power c to be big, so we can calculate b to the power c modulo something. But what would that something be? Would it be just m? No, it would not be just m. It would be something else, and that is given by Fermat's little theorem, right? So before I go on to Fermat's little theorem, let me check if there are any doubts. Not any doubts yet. If there are any doubts on the viewers watching right now, you can let me know in the chat. If you are understanding, and even if you are not understanding what you're saying, just say that I can't seem to understand. It's all right. I'll try to explain it again, or just write whatever you feel in the chat, right? So Fermat's little theorem is a very powerful tool used in modular arithmetic. What it says is a to the power p mod p is just equal to a mod p, right? If we actually allow a to be greater than 0 or a is not equal to 0, if we put that condition, then we can say that a to the power p minus 1 mod p is equal to 1. This is the better version. A to the power p minus 1 mod p is equal to 1. Right? This Fermat's little theorem here, p is a prime number, right? This is not any number. This is a specifically unprime number. Only in prime numbers Fermat's little theorem works, right? So you have to check if your p is a prime number or not. If you want to calculate, let's say a to the power b to the power c modulo m, right? If you want to calculate a to the power b to the power c modulo m, if your m is a prime number, right? If you check and it is in fact a prime number, then you can calculate b to the power c modulo m minus 1, right? And then let this be t, then you can calculate just a to the power t, and this would take the time complexity of just big O of log m. This would take a time complexity of big O of log m, and this would take big O of log m as well. Actually, this would take big O of log c, so let me put a big O of log c here. Big O of log c plus big O of log m, right? So why does this work? Why are we able to calculate a to the power b to the power c as a to the power b to the power c mod m minus 1? Why are we able to do? Let me write it properly here. Why are we able to do a to the power x is equal to a to the power x mod p minus 1 mod p, right? This whole is mod p. Why are we able to do this? Why can the exponent be modulized p minus 1? Well, if you see, x can be written as the quotient and remainder, right? If we divide it by p minus 1, so a to the power x is just a to the power some quotient into p minus 1 plus x modulo p minus 1, right? We break this term off, and that will be coming here. We analyze just this term, which is a to the power q p minus 1. That is a to the power p minus 1 to the power q, and we know a to the power p minus 1 mod p is 1. So this is just 1 to the power q, which is 1. Multiplying this with this, we get the answer, right? So this is why Fermat-Settle theorem is important, because it allows us to know. It basically allows us in the same respect that we were doing here. It basically in every step in addition and subtraction and multiplication, we are allowed to modularize A and B as well, right? We can modularize A as A mod M and B as B mod M, here as A mod M, B mod M. We can multiply this together to get mod M, but we cannot do A mod M to the power B mod M here, right? We have to do, this is actually wrong, we have to do A mod M to the power B modulo M minus 1 if M is prime, right? Mod M. If M is prime. If M is not prime, then we have another theorem which is called Euler's theorem. Euler found this very later after Fermat founded his little theorem, right? So Euler's theorem says that A to the power phi M mod M is equal to 1. Here M doesn't have to be a prime number, this can be any number. This is a more powerful theorem than Fermat-Settle theorem because M is allowed to be any number here. But what is this phi M here, right? This phi M is the Euler's totient function, right? First of all, before going on to the Euler's totient function, of course, if we have this Euler's theorem, then it would allow us to, you know, put A to the power B mod M as A mod M to the power B mod phi M mod M, right? It would allow us to do that. But what is phi M? Let us go on to that first. Euler's totient function is the number of numbers. It is a number of numbers which is greater than equal to 1 and less than n, basically between 1 and n minus 1, the number of numbers between 1 and n minus 1, which are co-prime with n. Co-prime meaning GCD d comma n is equal to 1. We say A and B are co-prime if GCD A comma B is 1, right? If GCD A comma B is 1, then A and B are co-prime, right? A and B are co-prime. So if GCD d comma n is 1, sorry, I thought my stream ended again. Never mind, it didn't end. So if it's just my tablet disconnecting. Never mind. So yeah, why is it happening? Just give me a second. Right. So right. So this Euler's totient function is pretty easy. Let me give you some examples, right? The Euler's totient function of 12 would be, I think 4. How many numbers do we have which are co-prime to 12? Less than 12? We have 1. We have 2 is 2 is not co-prime with 12. 3 is not co-prime with 12. 4 is not co-prime with 12. 5 is co-prime with 12. 6 is not. 7 is. 8 is not. 9 is not. 10 is not. 11 is, right? So we have phi of 12 is equal to 4, right? Similarly, we can take other for any prime number p, phi of p would just be p minus 1 because we have p minus 1 numbers co-prime with p, right? For some p to the power alpha, right? Let's say p to the power a. Here we would have 1, 2 up until p to the power a, right? We have all of these numbers. How many numbers will be co-prime with p? Will be co-prime with p to the power a? All of the numbers which do not have p as a factor, right? How many numbers in these many terms has p as a factor? There would be many numbers here which have p as a factor. Those would be p to the power a by p, right? So if we subtract from p to the power a these many terms, we get phi of p to the power a, which is p to the power alpha, p to the power a minus p to the power a minus p, which is just p to the power a 1 minus 1 by p, right? In fact, for any general n which is equal to p1 to the power a1, p to the power a2 up until pk to the power ak, we can write phi n as n into 1 minus 1 by p1 into 1 minus 1 by p2 up until 1 minus 1 by pk. Right, example 512, well, that is 4, we already calculated that. And this number is very important in modular multiplication, because the set of these elements, the elements that I mentioned here, this set, right, the size of which we are calculating as 5n, these set of elements are closed under multiplication. We'll see what that means in a short while, but due to that, this 5n number is very important in modular multiplication concepts, right? So this was Euler's theorem, which is m to the power 5m mod m is equal to 1. Let us come down to modular inverse, right? Here, modular inverse, what does modular inverse signify? If we have some ab mod m is equal to 1, then we say that b is just a inverse mod m. Basically, for any a between 1 to m minus 1, right, a inverse mod m is such a number b such that a into b mod m is 1, right? We call this number as the modular inverse of b modulo m, right? So using this modular inverse, we can define division as well. P by q mod m is just p into q inverse mod m. And another thing to note about modular inverse is modular inverse only exists when a and m are co-prime. Only when GCD of a comma m is equal to 1. If a and m are not co-prime, then the modular inverse doesn't exist. There are two ways to find the modular inverse, one using Fermat's theorem and one using Euclid's extended GCD. I'll quickly explain both of them. Both of these algorithms takes big of log m time, so using any of them is fine. Fermat's theorem just uses the fact that a to the power p minus 1 mod p, or let me actually take the general case, right? It just uses the fact that a to the power phi m mod m is equal to 1, right? So we can write a into a to the power phi m minus 1 mod m is equal to 1, right? So the inverse of a is a to the power phi m minus 1, and we can calculate that using modular exponentiation in big of log m time. So we have our modular inverse. We can do so we can calculate modular inverse using Euclid's extended GCD algorithm as well. We just have to calculate some x and y such that x into a plus y into m is equal to 1, right? Once we calculate such x and y, what happens is x into a is equal to wait a second. Once we calculate these numbers, if we take the modulo of this whole equation modulo m, we get x modulo m into a modulo m plus 0, because this is a factor of m, so this would be 0 is equal to 1, right? So a inverse is just x modulo m, right? So x and y can be calculated using Euclid's extended GCD, and whatever x you get here is just the inverse of a, right? So we have completed all of the beginner concepts that I would consider in number theory. There were a bunch of advanced concepts in there as well, like linear Diophantine equations, extended GCD. But from this point of time, we are just going to be going on the advanced concepts, right? From order of elements under addition, right? So let me quickly explain what do I mean with this. This is just you do not have to remember this. I just want to tell you what an order means, right? Let me explain what order here means, order of 3. If we add 3 onto itself again and again, right, we have 3. If we add 3 to 3, we get 6. If we add 3 to 6, we get 9. If we add 3 to 9, we get 12. 12 modulo 12 is 0. If we add 3 to 0, we get 3, 6, and so on, right? So we say that the order of 3 is 4. That is, we can go on to 4 numbers here, right? 3, 6, 9, 0. So the order of 3 modulo 10 is 4, right? let's take some other examples. What is the order of let's consider 5 modulo 8, right? So we have 5 initially, plus 5 we get 10, modulo 8 we have 2. 2 plus 5 is 7. 7 plus 5 is 12. 12 modulo 8 is 4. 4 plus 5 is 9. Modulo 8 is 1. 1 plus 5 is 6. We can just write it as 6. 6 plus 5 is 11. 11 modulo 8 is 3. And 3 plus 8, 3 plus 5 is 0. And then we get a 5 again. So the order of 5 modulo 8 is 1, 2, 3, 4, 5, 6, 7, 8. Right? Under addition. So what x exists such that order of x is equal to m modulo m? If we can have such an x, then it would be really helpful, because we can basically write all of these m numbers, right? Write all of these m numbers modulo m. Modulo m, we have m numbers, right? 0 less than equal to x less than m. We have m possible values of x's, right? So if we have such an x such that order of x is equal to m, then we can write each number y as just a multiple of x modulo m, right? So that would be really helpful. Does such a number exist? Yes, it does. And what is the simplest example of such a number? Well, 1. 1 is the simplest example of such a number, and we can just write each number as a multiple of 1, right? So this kind of numbers, which basically completes the whole set of numbers on which we are performing, is these are called kind of generators of this group, right? Generators of the group. The group that I'm currently looking at is Z12, right? Or Zn, right? Basically where I add the numbers modulo some n, right? So the generator of this group is 1. Or generator of mod 8 is 5 as well. It will also be 1, it will also be 3. Actually, the generators of the number of generators modulo m is 5m, right? It is the number of numbers which are co-prime with n, right? These are number of 5m. I'm not going to explain how we come up to so, because the order of elements under addition is not that important. I just want to preface this because I want to go next to order of elements under multiplication. This concept is important. This concept is important. Right. So same concept. We are just going to be multiplying the number onto itself and going to see how many elements can we reach. So let's try to look at order of 2 modulo 7. So we have 2. We multiply 2 by 2, we get 4. We multiply 2 into 4, we get 8. 8 modulo 7 is 1, and 1 multiplied by 2 is 2. Let's see order of 5 modulo 12. We have 5. Multiplied by 5, we get 25. And 25 modulo 12 is 12. So we go on to 12. Right? 12 into 5 is 60. And 60 modulo 12 is... 12 modulo 12 into 5. 12 in... sorry, I messed up. I was thinking about 13. So 5 into 5 is 25, and 25 modulo 12 is just 1, right? 25 modulo 12 is 1. And we can come up to 5 as well, because 1 into 5 is 5. Order of 7 modulo 12. So order of 5 is 2, and order of 2 modulo 7 is 3, right? Order of 7 modulo 12, that is 7. Multiplied by 7, we get 49. 49 modulo 12 is 1. And we can come back to 7 like that. So this is also 2. Order of 2 modulo 11, that is 2. Multiplied by 2, we get 4. Multiplied by 2, we get 8. Multiplied by 2, we get 16. 16 modulo 11 is 5. Multiplied by 2, we get 10. Multiplied by 2, we get 20. 20 modulo 11 is 9. 9 and multiplied by 2 is 18. 18 modulo 11 is 7. 7 into 2 is 14. 14 modulo 11 is 3. And 3 into 2 is 6. and 6 into 2 is 12, and 12 modulo 11 is 1, and 1 into 2 is 2. So what is the order of 2 modulo 11? It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10. Right? So as you can clearly see, we can never go to 0, because if we went to 0 at some point, we cannot come out of it, right? Basically, if we are picking a number which is co-prime to m initially, then can we have an order of x is equal to m minus 1 modulo m? Here m is prime, right? In the general sense, we want to find a number such that order of x is equal to phi of m modulo m, right? Because we only want to go over all of these phi m numbers where GCD is equal to 1, right? This is the group that we are considering. All of the numbers which are co-prime with m, that is the group we are considering, and the group operation is multiplication. So are there any generators of this? Now this is not such a non-trivial question. This is an actual important question. Does there exist a generator of this group or not? And in fact, as you can see from the start, there are lots of answers for different questions. If you look at M3, the generator is 2. If you look at M4, the generator is 3. If you look at M5, 2 is a generator and 3 is a generator, but 4 is not a generator, because 4 multiplied by 4 is 16, and 16 modulo 5 is 1. So we would just go from 4 to 1 to 4 and so on, right? For M6, we have the generator as 5. For M7, we have the generators as 3 and 5. 2, 4 and 6 are not the generators, because we would just go from 1 to 6 like this. We would go to 1, 2, 4 like this, right? Here in M8, we do not have a generator. There is not any generator here, because if we pick 3, it will just come back to 1 repeatedly. If we pick 5, it will just come back to 1. If we pick 7, it will just come back to 1. M9 has a generator 2 and 5. M10 has generators 3 and 7. M11 has generators 2, 6, and it has more generators as well. It has, I think 8 is a generator, and 7 is a generator as well. And yeah, these are the 4 generators of M11. 2, 6, 7, 8. M12 doesn't have a generator. M14 has 5 and 3 as its generators. M15, with this weird kind of loop, does not have any generator. And M16 does not have any generator as well. So this question of generator is answered by primitive root. Primitive root is just the question that we have been asking about now. Such x's such that order of x is equal to phi m modulo m, that is called a primitive root modulo m. And these primitive roots only exist when m is equal to 1, 2, 4, p to the power alpha, where p is some odd prime. P is a odd prime, or 2 to the power 2 into p to the power alpha, where p is some odd prime, right? And a is any number greater than or equal to 1. So primitive root only exists in the these 5 cases: when m is equal to 1, 2, 4, or p to the power alpha, or 2 into p to the power alpha. The number of primitive roots is phi of phi m, right? These are the number of primitive roots, and there is an algorithm to find it. It is a really easy algorithm, but I'm not going to be discussing it right now, because it's already 30 minutes past the deadline of this class. So there is this algorithm which calculates the primitive root and big of answer log phi m log n. You can find it on CPU algorithms. It is a really good algorithm. You should study it. And using this primitive root concept, there are a bunch of algorithms, bunch of questions that we can solve, right? Such as the question of what is a to the power x equal to b modulo m. If we have to solve for x, this is called discrete logarithm of b base a mod m, right? This is basically log b base a mod m, right? And this can be solved using a baby step giant step algorithm, and this works in big of root m log m. Again, not going to discuss it. You can find it on CPU algorithms. And another question that can be solved using primitive root concept is x to the power a b mod m, where it first finds a primitive root, then the baby step giant step algorithm is used to find the answer in this time complexity. Here we have to solve for x, right? So these are two concepts that I would suggest, actually three concepts: primitive root, discrete logarithm, and discrete root. Yeah, you should study these concepts in detail further going on. And some other concepts that you should study are Tonali-Shanks algorithm and Chinese remainder theorem. With the, Chinese remainder theorem is another concept in matrix uh, arithmetic, and it is a really basic algorithm. It is generally, studied a lot earlier, a lot it is studied basically in the early chapters of any number theory book, but in competitive programming it is generally regarded as an advanced algorithm. It is absolutely not such a complex algorithm, but it just happens to appear in advanced questions. So you should study Chinese remainder theorem. Tonali-Shanks algorithm, on the other hand, is an advanced algorithm, right? It is used to find the square root of b modulo m. Basically, answering the question of square root when discrete root when a is equal to 2, right? So x square is equal to b mod m. We solve that for any b. That is solved by Tonali-Shanks. Here it is taking a root m log m time, right? There it doesn't take that much time. It takes log m time, around log m time or log square m time, around those kind of things, right? So you should read these two concepts as well: Chinese remainder theorem and Tonali-Shanks theorem, Tonali-Shanks algorithm. Thank you for attending this class. I'll be looking at doubts right now, but before that, the next advanced level class is on Thursday 8 p.m. in 4 days. I will be teaching try and Aho-Korosik algorithm then. It would not be as cramped as this class. It would be completely advanced concepts, not basic concepts as well, and it will cover, Aho-Korosik algorithm, which is the multi-string equivalent of the KMP algorithm. If you have studied the KMP algorithm, which I think many of you might, it is just the multi-string equivalent of KMP, and it is a really good algorithm which uses tries and so if you want to read that, you can if you want to learn that, you can attend the next advanced class, and the next beginner level class is on tomorrow. If you have a beginner a friend who is just starting out in CP, you can recommend him the beginner level. The class that is going to be conducted tomorrow is greedy algorithms and 2 pointers. So you can absolutely recommend someone who is in need of learning these concepts. Anyways, thanks for joining this class again. You can find the relevant links down here. This is the link to follow any and all updates regarding SnackDown. It also includes this prep series and some prep contest on snackdown.codechef.com, and it also includes all of the dates